Welcome to the module 6.2, modeling cellular force with links. So here we'll be doing some new things in CompuCell3D that you may have seen in the guest talks from end of last week, okay, where you actually add active force within the cells, okay. So I like to start this module uh, with a video of convergent extension in Zebrafish. So before I hit play, I want to take a quick look at this and describe the chat everything that you're seeing, what's going on in this video. So let's please take a look at this. Okay, so what you have been seeing here is the development of a zebrafish embryo, starting from the epibole until the formation of these structures called somites. So if I play it again, you see that you see a lot of cell process movements. First, you have cell grow and spreading towards the center. Then what you start to see some kind of cells going towards the center of the structure. So the cells are going this direction, expand in this direction. Then you start to see a form structure. This is going to be the notochord. And then what you're gonna start happening from the top to bottom is the formation of these rosettes here. It's not really rosettes, they are called somites. We're going to be the precursors, your vertebra, and many muscles in your body axis. And then you see that also you see cell division, cell growth. Here you start to see a little bit of neural tube formation, which you're going to form the spinal cord. So what you'll be seeing here is that uh, Settling for biology, morphogenesis is a very active process. There are a lot of cell movements. And for order for all this to happen, the cells must exert force on the neighbors, pull on the neighbors. The cells be able to be stretched, respond to those forces, or just resist those forces. And sometimes these forces are be anisotropic. Sometimes it's going to be just along one direction rather than the other. And that can lead to the migration of the tissue, as you see in the beginning, going from the top to bottom. You can also, and also if all the force that cells act on the neighbors are along a specific axis, that can lead to a process called convergent extension, where the cells start to interdigitate between themselves and the tissue as a whole converge along one axis and extend along the other. And the cells can also start group together, make forces with some of the neighbors, not others, to form this kind of structure that you see here more towards the end. That's called the somites. The cells can also stack on top of one another for the notochord. So all this requires that the cells, there are a lot of forces on their neighbors, okay? And it's usually along a specific direction, okay? And that's something that can be implemented in CompuCell3D by the use of spring-like force between the cell centers. So you already have seen this in a few of applications. Uh, So I alluded that in my subcompartment model, where the cells in red along the apical side, they are exerting force one another. This is done by use the links. Here you see another application of the use of those links, where the cells, they have some very strong links between themselves that are modeled by spring-like force between the center of masses, and at some point this becomes compromised, and the blood vessel that's in below can start to invade in and do the detachment of this kind of layer. So this is a model of um, choroidal neovasculation. And here's another model where the cells first undergo a mesenchymal to epithelial transition, and once they cell polarize, they start to elongate, and that again is using this kind of concept of links between the cell compartments in this case. But here The cells also have kind of link-like forces along their apical sides, which in this case, in this example, are in green, and that leads to this wedge shape that forms those. Um, that gives the typical curvature of this epithelial balls that form. So all these examples are done with links that you add between the cells, and that's going to be the subject of this module 6.2, where I'm going to cover the basics and do a few exercises, and also module 6.3 after um, the the interval, where I'm going to be talk a little bit more applications. So here's the plan of action for today. This module gonna be us to introduce the how you make those links in CompuCell3D, and we call these links focal point plasticity or FPP in shorthand. And we're gonna do overview of how they work, okay, a simple exercise to how they work and how you can manipulate that or set the parameters at XML level. We're gonna first do that with a simulation with only one type of cell links, and then you can do that with a simulation where you have two cell types, and then you can actually change the links between cells of same time versus different types, and we can maybe do some kind of cell mixing or sorting, depending on how you chose those parameters. Then you're gonna have an interval, and then you go to a module 6.3, which is going to be slightly longer. So 6.2, I maybe gonna take 45 minutes to go over that, and then it's gonna 6.3 gonna be a little bit longer. And on 6.3, I'm gonna do over applications. I'll show how you can manipulate those links at the Python level to do more specific link manipulation. And then I illustrate that with two examples of cell crawling using links, one over different cells, another over substrate, and then I end up with an example how you can use that to model convergent extension of tissues in CompuCell3D. Okay, so that's the overview for and the plan for today. So let's start with the first part with model 6.2, the FPP links basics. So again, if you have any questions, please send a message in the chat or interrupt me or raise your hand, and Hayden can unmute you. And please, to keep it interactive, send a message in the text in the chat to tell me that everything's okay, or if you need a pause or you need to explain anything again. I'll be happy to do so. So as I said before, the FPP or the focal point plasticity links, they connect the center of mass of two cells in your simulation, right? So usually that's modeled as a classic Hookean-like or spring-like link, where the force scales with the distance square from a specific target resting length between that links should have. So that is what the energy term should look like uh, on the Hamiltonian. So the two holes are the row from the first cell, and their hole prime is going to be identify the second cell, and there's going to be a force that's going to set the strength of the constraint, the link constraint. This little d here is the distance between the two center of masses. Okay, so that's giving the two cells that's gonna tell exactly what's gonna be this distance here. And this d targets should be the resting length that the center of mass should have. Or if the cells center of masses are separated by this distance, then this difference is going to be zero, and the cell experience no restoring force to the center. If this distance between themselves are a little bit longer or a little bit shorter compared to what the ideal distance that you set up between those two cell center of masses should be, then the cells will experience a restoring force that either bring them closer together or bring them further apart from each other, until the actual distance between the cells are the target distance between them. So all those, uh, so both this term here, the lambda FPP and the target distance, are parameters that you set up in your simulation in the XML level. So you can set up how strong those strain will be and what should be the ideal target distance. So both of those two terms is under your control, and you can you choose what the values will be, and both of them have to be a value that's positive, right? So the string has to be a positive number, how much force you add to restore. If you make that 0, that's you're basically turning off that constraint. And the target distance again has to be a positive number, and there is no direction in it. As long as the center of mass satisfy the condition, they experience a zero force. And if they are further apart, then it should be, or closer than it should be, then it will be a restoring force that places the cell back together to the correct place. So does this make sense? Let me know if you have any question in the chat, or just said that everything is fine and I can proceed on how you can work that on the wizard. So everything is fine. Let me show how exactly how you implement that in your simulations. Okay, so you'll be creating your own simulation. Usually we do that through the wizard. And when you are in the wizard, what you have to do, you have to select the focal point plasticity check mark here on the cell behaviors, and then you're going to activate this plugin in your simulations. Oh, good question. If I increase the value of lambda here, would that mean that cells are less deformable? Yes and no, because what you are increasing is the constraint between those two cell pairs. Okay, the cell can still be very deformable, but the two cells cannot be brought further apart or closer together. So if you have just two cells in a link, as you see in this example, the cells can still be deformed. There can still be a force that make those two cells go down or go to the left or go to the right. So they're still deformable, but they're coupled together very strongly. So where one go, the other has to go as well. Okay. If you make the lambda less strong, then what that means that you are free to move one cell or deform one cell without deforming the second cell. Okay, so it's this will be the case when you have just two cell links. Of course, when you have simulation where you have multiple cells, they're confluent, and all those cells are linked together, then yes, then increase the lambda, you make all those links more strong, and then the tissue as a whole will be less formable. So you cannot slide one cell, the cells will not be able to swap neighbors places. So if you make the whole tissue less or more deformable, it depends on how many cells you are in your system and how is the connectivity between them, because that's something that you play with. You can set that each cell have at least one connect, at most one connection with a neighbor, or can have at most six connections to a neighbor, which in 2 dimensions is going to be all the neighbors, or maybe can have four, can have three. So you can play with all those parameters and make the tissue as a whole more deformable or less deformable. Does that answer your question? The biological analog to links will be the focal adhesions, the desmos zones that connect the cells. So the desmos zones are kind of focal adhesion that usually connects the intermediate filaments of the cells to each other, and they usually just hold the cells together. Intermediate filaments, they do not exert force, but they can resist the forces. So you can think of these FPP links as this established focal adhesion that connect the cells center of mass to a neighboring center of mass. Okay, so once you tell the CompuCell3D wizard that you want to have focal point plasticity plugin turn on, and you hit to create a simulation, you see towards the end simulation a lot of plugins that comments that look like this. You have a plugin named focal point plasticity, and depending on which cells you have to simulation, you automatically populate all the possible cell pairs that you can have. So it's going to be parameters, type 1, type 2. So this is going to be the cell types that you have in your simulation. And then you have all these kind of parameters that you can choose for the specific pair. And if you have cell A, cell B, you're going to have another set of parameters that's for cell B and cell B, and cell A and cell A. So they can be is specified by cell pair, so you can have all the possible combinations. And the first time you do this, you can also see internal parameters, and that's the same links concepts, but for the case when you have internal cell compartments, as I talk to you on Friday morning. Okay. So before I go to this, let me read the next message in the chat. What's the visual difference between link works and gap? They both seem to represent distance between cells. Is a difference that links works measure the distance between cells' center of masses, while gap measures the distance between their boundaries? Okay, thank you for the question, Isis. Uh, the gap is a parameter that you put on the in the uniform initializer, right? So you create the cells instead of have the cells kind of conflict one with one another. You have a little gap between that. So that's just a concept that's used for the initial condition. As soon as you start simulation, that gap can either widen because the cells are going to move further apart, or they can be closed because the cells get together. So that is just used for, in the uniform initializer to set the initial conditions. The links, they're going to actually connect the two cells, okay? The links actually can work even if the cells don't touch each other, okay? You can still have the link that, then you usually have to set up by the Python level, but they just kind of lock what should be the distance between them. If you make the distance between the two link, the target distance of the link to be much bigger than the typical cell radius or the cell diameters that you're connecting, then that link can force a gap to appear between the two cells. So yeah, that can happen. Or you can also set the target distance between the two cells through your link to be shorter than the typical distance of the cells. In this case, you can actually be compressing the two cells together, and there will be, and then you cause deformation. Okay, so if you set the target distance of cells to be exactly the sum of the two radii of the two cells, then they're going to be happily together. If you make set that to be much bigger than that, then you cause the cells to separate. And if you set the target distance to be smaller than the sum of the two radii of the cells, then they will be compressing the cell. So going back here to the terms, okay, let me first specify where the lambda and the target distance are appear. So the lambda, which is going to be the strength of the link, okay, appears here, okay, is this lambda, and here set 10. And usually, as a rule of thumb, you want this value to be in the same order of magnitude of the temperature that you set up in your simulation. So if you make a simulation of temperature 10, you usually use a lambda 10. If you make a simulation of a temperature of 100, you make this 100. So that's more or less how you should choose the value here. Of course, as you put your simulation, then you can make this stronger or weaker until you get the desired behavior that you're trying to model. And here, target distance is the target distance between the cells. Usually, our cells are about 7 pixels or lat sites in length, right, in diameter. So, and because you be connecting two cells together, usually you start with a value that's about the diameter of the cell, which is 7. So two cells will be happily bound together at a target distance 7. If they're 7 by 7, right? You put two cells together, the typical distance is going to be 7 lattice sites. So at 7, the cells are happy together but connected. They cannot move apart and cannot get too close in, right? And then while you have some other numbers here, okay? The other two that are, or three that I want to specify. First is that these parameters are by cell types, okay, pair. So here I have a cell type my cell, another cell type my cell. If you have a cell type A and B, is for by the pairs, okay. Here, this value here is also very important. It's going to be the maximum distance. So what does that mean? That means that if you start to bring your cells further apart and further and further and further, okay, um, at some point that link should break. Okay, so if you have any kind of spring, right, and you start to move the spring around, stretch the spring, at some point the spring breaks, and you don't have a connection anymore. So that what this maximum distance means is the distance at which how far you can stretch your two cells before the connection between them is broken and cease to exist. And after that time, once that exceeds, the link breaks and there is no more constraint between those two cell centers. They're free to move around independent of each other. So that's what this maximum distance is. If you make this maximum distance very, very big, the size of our whole lattice, that means that the links will never break. And if you make this maximum distance be very close to the target distance, that means that any deviation, small deviation from the ideal, you break the link. Okay, and that's something actually that you might want to do in our simulations. Okay. Now, the other thing that you have to pay attention is this kind of number here, which can be the maximum number of junctions. Okay, so here under this tag, you have two numbers. You have the neighboring order, and which is set to 1, and the maximum number of junctions in this example is also set to 1. The important one is this one here that I circling with my cursor. So if you see my cursor, this number here sets how many links a cell can have with another cells of that other type. So if this set to 1, it doesn't matter if the cell has many neighbors, you're gonna only make a link with one of them. If you set this to 2, then you're gonna make 2 links at most. If you set it to 3, you're gonna make 3 links at most. And if you set it to a 10, then you can make 10 links at most if you had that many neighbors. Okay. This first number here, neighbor order, is how far the cells have to be before they create a link. Okay. So this is also a very important number. So in many cases, your cell can only have 2 if you're making modeling epithelium, right? And a cross section of epithelium where your cells are side by side. Okay, then you want your cell to have at most 2 connections to the cell on the left and the cell on the right. Okay, so then you set this maximum junctions to be 2, for example. If you're modeling epithelium in 2 dimensions, right, the plane of the epithelium, then you probably want to have the set maximum which happens to be 6, because in our very well packed epithelium, your cells usually see 6 neighbors. So you set that to 6 or maybe to 7, in case there's some inaccuracies in the packing. So you choose a number in accordance with the structure that you want to model. Okay. Okay, say that a cell, a very good question by Ildis, Robert. Say a cell can only form one link because it's at 1 here, but it's surrounded by the 10 neighbors. How does it choose which to form a link with? As you do as far as I understand, as you do as the cells start to interact, okay, by doing those lattice copies attempts, okay, the first cell the first neighbor that the cell interacts with by a neighbor copying pixel, you form that first link. Okay, so is the criteria is by first interaction. So as you're doing the lattice side copies, every Monte Carlo step, the first interaction that it has with the other cell, it makes the link. Okay, so it's random somehow. Of course, if that other cell already has a link, right? So you're already satisfied its maximum rejunctions, then you cannot do the connection. Then it has to be if one of the other 9. Does it make sense? So basically, it's going to be random. Okay, great. So about this kind of link formation, right? That's where this neighboring order and activation energy come into play. Okay. This is used for the creation of links. Usually you don't have to worry about that. Any all the examples that we're gonna cover today, you don't have to worry about it. But just for completeness, I'm gonna tell you exactly how it works. Um, Usually when you create a link, right, you are adding a constraint to your cell, okay? And usually the constraint increases the energy of your cell, of your system. So usually the creation of a link is something that you think about the metropolis algorithm or or in a concept of energy minimization is something that should never happen because the creation of link increase the energy of the system. So it should be highly unlikely that you uh, the link should be created. Okay, So to make this creation of the link more likely, you have an activation energy set up to have an active number. So when the two cells interact together, right, you offset that initial energy increase by the activation link by an offset of, in this case, minus 50 energy units. Okay, so the links are more likely to be created than not. Okay, so that's what this activation energy means. And usually set up to be minus 50 is already fine, and you're gonna create all the links, so don't have to worry about it. And this neighbor order that you see here and here is how close the cells have to be together before you attempt to create a link between them. So a neighboring order of one means that the cells actually have to be close together. A pixel of one cell, a left side of one cell had to see had to be close to the left side of the other cell, so they had to be uh, have a neighboring order of one. But if you set that to be a higher number, like 4, 5, or 7, then as soon as the cells get close by to other one, they can already activate a link between them. So that's what it means. So this neighboring order. And this is going to be a general neighbor order for all the possible links that you can create, but it can be overridden by a different neighbor order for a specific cell pair. Okay, another question from Neher. If I only want type 1 to form link with type 1 and type 2 with type 2, should I also introduce this in the XML? Yes, excellent question. That's going to be our second exercise today. If you have, um, you specify, okay, well, when you set parameters, right, type 1, that's just an entry, and type 2 is just an entry. Here you actually specify the name of the types, okay? So let's say you have type A and B, right? So that gives you three possible pairs, AA, AB, and BB. And if you only want AA and BB to happen, so what you have, oops, you have three sets of blocks of these parameters. The first one will have AA, the second one's gonna have AB, and the third one is gonna have B and B. So what you do, you set the BB, A and B, which is the one that you do not like, to have zero maximum number of junctions. Therefore, they're never created. And then you set AA to have one or more, and BB to have one or more. So you're going to have AA links, BB links, but not the cross links between them. Does it make sense? Yeah. So we're gonna do our second exercise will be exactly that. So if anyone didn't get it, my brief explanation now, we'll be coming back to that in a few minutes. Okay. So how you do that in the actually, let's now start with our first exercise. So this is going to be exercise 6.1.2.1. Okay. Simple model with links. So again, you can either try to code along, which I suggest, but if you do not want to code along, because then you can just download the 6.2.1 zip file in the shared folder that Hayden share with you. So let's all now open the wizard, go to CompuCell3D project and click new CompuCell3D project. Okay. Thank you, Hayden, for sharing the module slides and the demo codes. So let's do all here. CompuCell3D, new project. Click here. Once you click here, you get you have to give the name. Let's call it links, simple, okay? And make sure you have Python plus XML selected here. Now you hit continue. Once you hit continue, it asks to the size of the simulation. Let's just leave everything as it is. No changes here. Okay, 256, 256, no flux, rectangular slab. Okay, and let's hit continue. So hit continue. If you missed the previous instruction, they are still kept here as a memory what came before. So let's hit continue here. Now you go to the cell specification. Okay, we have to give a cell name. Your cell type can be just A, or it can be my cell, or it can be whatever name you want to. If you want to name your cell after your dog, you just add the name of your dog here, and it doesn't matter. Okay, so what it matters is that you add the cell type name and hit add so it appears in the table here. Once your cell type appears in the table, then you can hit continue to the next window. So make sure it appears here, hit continue, okay? And once hit continue, you have to select the cell behaviors and properties. Let's select the contact, the volume flex, center of mass, cell neighbors. I think they are all selected by default. But the most important thing here is to select focal point plasticity. Okay, make sure that this one is selected. Uh, Once you make sure that one, then you can hit continue. Okay, let's do this. And then you get to the chemical fields pop-up box. You ignore them and hit continue. And then we go to the contact and contact internal window. Let's set the neighbor order to 4 here. Okay. Uh, the default now is 2, but the 4 is the one that works better for two-dimensional simulations. Okay, so make sure that you make this back to 4. And once you set up to 4, leave all the energies as they are. Okay, we are not worried about them. And then you hit continue. And once you hit continue, you're basically done with simulation. Okay, and everything's fine. So neighbor order 4 here, hit continue, configuration is complete, okay? If you have not done this, you can just download 6.2.1 zip and open tweet it, and you have exactly what we have here. So, um, so here are all the informations again. Just now hit right click on the name of the file on the wizard and open in player, and let me know if you what you see and if it's working. And how many links each cell has. So only Robert saw the links and Hagu also. Okay, so let me go to the next slide. Okay, so what you should see is something that looks like this with only one link per cell. Okay, so you only make links of pairs. Okay, many of you have not seen the links, and that's not necessarily means that your simulation is not working. It's probably because you don't have the links visualization set up for you. So if you do not see the links, go to the 3D visualization. It should be the cell player visualization, and make sure that under visualization the FPP links is selected. Okay. Once you click this, then you should be able to see the links. Do you see now? Everybody that did not have the links before. Okay. Shamayeta has. Okay, we have. Varga has. Okay. Okay. Levi or Levi has. Nehar has. Okay, everybody see the links now, right? If you, again, you know that you can change the cell colors, right? If you have a cell colors like Hannah, and let's say that Hannah really likes her cells to be blue and her borders to be yellow, but of course a link that's white does not work very well in her simulation. So what you can do, you can click on this icon here on simulation and select the FP link to have a different color. So it can have the links as black or as pink or as blue, just like what you, who did the black links? Hagu did the black links. That's fine. Okay. So you can change the links. Okay. And it's important for this exercise that your links will be very well visible. So either choose a cell color that's a little bit darker, or make your link to be black to send out a lighter cell color. Okay. So did everybody got here? Okay. So let me know. So let's talk now now the visualization issues are solved. Okay. Uh, what's going on here? So let's talk what's going on here. So what you see is that every cell has at most one link. Okay. And because if you look at your XML code, you see that your maximum number of junctions is set to be one here. Okay. So that's why every cell can have at most one link. Of course, sometimes uh, a cell may everybody has been taken and the cell cannot find any pair. So you have some kind of lonely cells here that cannot make any link because it did not find an available neighbor. Okay. So that can happen by chance. Okay. Yes, there are some cells without links. Okay. It's very sad. So one thing that you can do, you can fix that by just increasing the max number of junctions. So that's going to be our first exercise. I want you to increase that to 2, 3, and higher numbers. And let me now place in the chat what kind of link topology that you see in your simulation. Okay, so please try to do this. Change this parameter, maximum junctions is the second number, okay, to 2, 3, or higher, and tell me how it looks like. All right, Vargas, share something. Let me look at your image. Your image, let me make it bigger. It seems that you set up the number to 2. Every cell can have at most 2 links. Is that correct? Aritra also set to 2. Okay. Uh, okay, all the examples so far are set to 2. You can set to 3 to see what it looks like. The nice thing about the 2 is that you basically create a maze, right? So you can use this as a maze creation. If set to 3, now it's as Kyle did and Levi. Now it's like a little bit hard to find a path that goes from one side to the other side. Okay. Even if two, so what you can do now, right? You know which cells are connected to each other, right? So you can ask questions about or explore effects of rigidity percolation. Okay. How many links should you have before there's a continuous percolation path from one side of your system to other side? If two is very hard to find, okay. Uh, Actually, in the example from Snigda, there is one path. I just found one by chance, but I don't think there is such one by Aritra. Okay. But if you do 3, right, then already you can go from one side that you satisfy percolation of links from one side to your system to the other. And of course, you can keep increasing that. Okay. Uh, but just because the links percolate, that does not mean you have a rigidity. You can still kind of move the cells around if you extra external force. If you have something like 4 or 5, then probably now all cells connected, it's going to be very hard to add a shear force that and the whole tissues are all should resist. So, and of course, if you do 6, then everybody connected. Okay, so you can see that there's some kind of soft matter or tissue rigidity and fluidity thing that you can start already to explore with the concept of links. Okay, so let me go to my next slides. Here I have a snapshot of how the simulation look like at different kind of levels of connectivity or when I set up the maximum number of junctions. When I set to 5, most of the links are connected. When I set to 6, then cells pretty much make make links with all the neighbors. Okay. So you probably got all of these kind of behaviors or outputs there, right? So that is for you to explore what one of the parameters uh, in your XML file that you have control of. Okay, the link function will be random, but sometimes you want them to be random, so then you can explore these kind of things. So we still have another parameter that's very easy to play, which is going to be the target distance within the length cell. So right now, outside makes links, okay, but they are happy where they are because the cells typically have a diameter of 7. So the typical cell distance to distance, center to center, this can be also be 7 pixels, okay? But you can make that shorter or can make that bigger, that this target distance. So let's try to do that. Now let's go back to your simulation. Let's set a connectivity level between 2 or 3 for better results, no more than that. And now try to play with the target distance between the cells. Okay, do that and tell me what happens first when you make them shorter than 7, and then later what can happen when you make them bigger than 7. When you make shorter, make it really short, make like 2 or 3 pixels. Okay, and let me know how it looks like. You can also do that direct on the player. So the player you can change the parameters right there. So that's more fun because you can see the effects right away as you do them. The activation energy right now does not really affect simulation because we set to a very negative number. So all the links that can be created are created. Okay, so there's no huge effect. Okay, that is so what I want you to do first is set the target to very small. You can even set the target distance to be 0. So ideally the two cells should overlap, okay? And if you do that, what you expect is that your whole tissue should kind of compact a little bit. You will not be completely compact. You will not go too much because you also have the volume exclusion, right? The cells have a target volume, but you make all your simulation tense. But the most striking outcome is the one that Robert did, where he made the target distance to be much, much bigger than 7, right? If you make 10 or higher, what you start to see is that the cells start to spread apart and things pretty much explode. So let me show a picture of how the things look like. So I think on here I have a target, a maximum number of junctions of 4, okay? And this is going to be the normal output. The one on the left is when I make it smaller, okay? So then the tissue, you cannot really see, but the tissue is a little bit more compact. If I make it slightly bigger, like I make instead of 7, I make a 9 or 10, then the tissue starts to be a little bit rough because now the cells actually don't want to be next to one another. They want to actually have a cell in between. And if I make the maximum distance to be, the target distance to be to far exceed what the typical cell diameter should be, right? Then you start to have this kind of more striking outputs where the cell just kind of spreads like that, as you see here. And these outcomes are better seen if you have a maximum number of junctions to be 3 or 4. Then you see these outcomes. Were you able to get things that look like this or that? If you did, please share your pictures in the chat. Levi. Okay, Levi, you went a little bit further, okay? More extreme. I can already see that Nathaniel was a little bit more cautious or maybe made up target distance. So my guess that you set up a target distance of 20. Uh, of course, your target distance is higher than your maximum distance, then the cell's gonna move apart and break the link. So that's gonna be one effect that you can have. They move apart and break, move apart and break. Target this of 3 with 3 maximum links, the cells should kind of compact a little bit more. And that's what you see in that's in the snapshot from Barga, Barga Prasad. Okay. Oh, Shivani got something that almost looks like a copy of my setup. So you probably use the same parameters that I use for the one on my slides. Okay, they look very similar. Okay. Okay. All right, very good. So this is the what I have in mind for this first exercise. Do you guys have any questions? So that's everything that you can do with just one cell type, right? You have just 2 parameters that you can play and see the effects, the maximum number of junctions and the target distance. You can also play with the lambda, okay? So for example, if you set all the target distance to be 0, right? And you make your lambda to be 100 or 1,000, right? Then you're gonna choose really see a compaction of your cells, okay? Because now you'll be overcoming the target, the volume constraint, and everything should be kind of more compact, okay? So that's something that you can also play with. So let's go now to the second exercise, 6.22, when you're going to explore what can be done when you have two cell types and you connect them with links. And those two snapshots that you see in the screen is the things that you'll be doing for this exercise, okay? But before you get there, let us make up the setup, all right? So we're gonna move to a slightly more complex exercise. Okay, we have two cell types, and I want to create a simulation again for links. And the cell types for convenience, I'm gonna call them G and P, which stands for green and purple. So let's do this. Okay, let's create simulation for links, the two cell types. So please, everybody, go back to Tweedit, click on New CompuCell3D project, and create a new simulation. And let's call simulation two cells. And please go by yourself through the wizard and create a simulation with two cell types, one called G and the other called P. And you can leave everything as you get automatic on the setup. The only thing I'll ask you to change is to make the neighboring order to be 4 instead of 2. Okay. Once you, so please do that. And as you do that, you should eventually get XML code, and your XML code should have this kind of 3 terms in the focal plasticity link. Okay. So I'll give you 1 minute to set up the simulation with two cell types. Okay. So that's your exercise now. Make a new simulation with two cell types and call them G and P. And let me know when you all got to that point. And if you don't want to go over the wizard, again, you can just download 6.22.zip, and you already have the setup simulation created for you. Okay. Robert got it, and I can tell that Robert already is doing something. Okay. Shamaita did, Kyle did. Okay, excellent. So you got simulation, right? So before you play with the parameters, uh, I want you to take a look at the XML code, okay? And uh, in your XML code, if you go under the plugin Focal Point Plasticity, you should see the entries that control the interaction between G and G cell types, G and P cell types, and also P and P cell types, okay? However, you might see more of them. Instead of 3, you probably are seeing way more. You also because besides the parameters, you also have internal parameters, right? So if you see any internal parameters tags under your focal point specific plugin, you can delete them because we're not using some compartments in this example. Okay, so delete all internal parameter tags. Delete all internal parameter tags. Okay, because we're not dealing with sub compartments. The other thing that you may see if you're using the CompuCell Player 3 4.9 is that there is it's not a bug, but uh, yeah, it's kind of a bug in the wizard because it also defines the parameters between the cell pairs and the medium. Okay, so you might see parameters cell type 1 to be medium and cell type 2 medium and P and medium and G, right? So they should not have been created. Okay, so that's um, a bug that was introduced in 4.9, unfortunately. So I'll ask you also to delete all parameter tags with medium. So it makes no sense for a cell to have a FPP link with the medium, right? They will not even work. Okay, so if you see any medium here, you can just delete the whole thing. So in the end, you should only have those 3 blocks of code inside the plugin between GG, GP, and PP. So now that you all see this only three tags here, GG, GP, and PP, and they should be parameters, not internal parameters, okay? Let me go, what's going on is that if one has its own lambda, each one has its own target distance, and each one has its own maximum distance, and also its own max number of junctions, okay? So the first one will be control the GG pairs, second going to be the G and P pairs, and the last one is going to be the links between purple and purple cells, okay? So that's what you want to do. We'll be playing with. I see that Barga has green and blue cells. You can change if you define them as G and P, you can maybe recolor your cells, okay? So you know what one stands for. And the same thing for Kyle. You might have a purple cell, but no, you actually have a purple and a green cell. They're just kind of lighter than the one I have here. Okay. So now that you have this simulation, you see that you have total control about how many GG pairs, PP pairs, and GP pairs can have, and what can be their parameters. So now that you have the basic file working on, my exercise or my challenge to you, okay, will be to create, modify those parameters to create simulation where you induce mixing between the cell types and then find another set of parameters that are going to induce sorting between the cell types. Okay, so if you want to have a kind of checkerboard pattern of green and blue cells, okay, sorry, green and purple cells, what kind of parameters you should choose for each one of the cell pairs, and which kind of cell pairs you have to turn off. And now, what if you want the reverse? What if you want the cell sorting between the cells? Okay, which kind of parameters you have to choose, which cell pairs you will allow to make and which cell pairs you will not allow to make. Okay, so I'll let you now to try by yourselves to get a first try to the cell mixing, because I think that's the easiest one, and the cell sort is a little bit more complicated. So basically now change your parameters until you get something that either looks like this or that, as I show on the starter slide of the exercise. So try to do your parameters, exploration, think about what you should be working on, and then keep trying. And when you get something, please share with everyone and tell us which kind of parameters what you have done in your simulation. Okay, so that's now on you. And I see that one of you has already got some mixing. So Hegu, what have you done to get the mixing of the cells? Tell us in the chat or unmute yourself and tell us. Turn off interaction between GG and PP and just left the P and G on. Yeah, that's a good recipe. So GG and G, they do not interact and actually do not interact. You want to promote the G and P interactions, right? So you just turn off the others. Okay. Uh, Do you have any choice on the how many GP connections you can have or the distance? Or did anyone else got the sound mixing to work? So one thing that would be very good to a trick that you can use in these simulations, if you want your links to be very dynamic, to form and break very often, okay, you probably want to make the maximum distance to be very close to your target distance. So usually here the target distance will be 7, right? And because usually the cells are about 7 lattice sites apart from each other because that's the size of the cell. So if your typical distance between cell type cells is around 7, and you want to allow the very dynamic creation and deletion of links, you can set the target distance, the maximum distance to be 8 or 9, and this means that it's going to be very easy to break a link and form a new one that's more favorable according to your instructions. So, and that will be especially helpful when you try to model the cell sorting, the second outcome here. So for this other one, I already suggest that you use a maximum distance of 8 or 9. so you can create new links more easily. Okay, Neher got a really good mixing there. Ah, okay. Well, Neher got mixing and you did something different. What did you do, Neher? You found another recipe for some mixing. Increase the energy from 15 pp to 100. Okay. Okay, I thought that you would have actually increased the target distance between purple and purple to a bigger value. Because it seems that the purple are actively pushing themselves from each other. Aritra, can this because self-sorting is going the right direction, but it can be made better. Okay. But yes, you turn off interaction between G and P, yes, and increase neighbor order between no, don't change the neighbor order. Change the max number of junctions. I think that it can be a better outcome. Okay, I got really good sorting. Okay. GG and PP are equal, and they have a lambda of 7. I don't know if it's lambda or distance. And GP is 30. So Kai, are your 7 and 30 the target distance or the lambdas? Target distance, yes. Okay, so that works. Ah, okay. Neher, you use the energy of contact, the contact plugin. Okay. Yes. If you change the energies in the contact plugin, you get self-sorting. Uh, but the challenge here is trying to do that without using the energy. Okay. Is doing that only with the links. Yeah, for sure. If you change the cell energies, yes, you'll get cell sorting. But try to do that if you only manipulate the numbers in the links. Okay. Okay, Bragda Prasad also got cell sorting. All right. So you already 1 hour of class. Okay. Let me just share with you what I did. Okay. So for the cell mixing, this is how I model it. Okay. The first thing, and many of you did the same, I completely turn off the links between green, green, and purple, purple because I don't want any interaction between them. And I set the darkest distance between green and purple to be very one. So they really want to push each other very close by. And I make the maximum distance to be 7. So it's very easy to break links between them so the links are more dynamic. Okay. And I set the maximum number of to be 3 because I want a checkerboard pattern. I don't want necessarily a green cell to be completely surrounded by purple or vice versa. So I set the maximum numbers to be 3. Okay. So that's what I chose. And if you choose, and if you type on the same numbers, you'll get the same output or something very similar. And if you want a copy of this file 6.2.2a have this implemented. And for me to induce the self-sorting, okay, that's what I did. First, I turn off the green and purple number of junctions that they have allowed 0 junctions between them, okay? And then on this example, I try to have the greens to be inside the purple, okay? So I want the green side and the purple outside. So for this one, I make the green connections stronger, so they can have up to 6 neighbors, right? The target distance is going to be 1. Maximum distance is going to be 7, so going to be very dynamic links, okay? And I increase the strength of the green, purple, green connections to 15, so it's stronger, okay? And the purple, I kept the string as it is. Also, they want to connect close to each other. So a target distance of 1 lattice side and a maximum distance of 7. So again, very dynamic link. So it's very easy to break and create new ones. But because I want these cells to be outside, okay, of the green ones, I make the lambda to be a little bit weaker than the green. And also I limit the number of junctions to be 3. Okay, so I favor the formation of kind of uh, trails like this. Okay, so that is the choice of parameters that I chose for my cell sorting. It kind of works, but you can also have other stuff like Arteta just shown here, and also Nathaniel shown and Kyle shown. They all work. So there are multiple recipes for you to get either cell sorting or cell mixing. Okay, and but the idea of this exercise to make you uh, more familiar with how links work, how you can manipulate that from the XML. And we have not even gone into the how to manipulate them from the Python level. If you want to go to Python, we can do more stuff, but that's going to be for the next module in a few minutes. So this is everything I want to show for this first part for the basics. So I will stop here and we can already open up the questionnaire, and hopefully that was useful for you. And in half an hour or after interval, I'm gonna go through the some applications, how we can model cell crawling, how we can make links not between cells but also between the cells and a specific point in space. Okay, so that would be anchors, and we can also and we're gonna make two models of cell crawling and also a model of convergent extension of tissues using the links. Okay. Okay. So with that, I'll stop here. Please fill up the questionnaire.